Hey guys, so today we're going to do chapter 6, section 4, which is all over the multiplicative inverses of matrices. So we are going to start off by talking about the multiplicative identity of a matrix, which is the matrix that you multiply any other matrix by to get itself. So when let me get the color chalk. When we talk about numbers, we talk about the identity as being what do we multiply a number by in order to still get itself? Well, that number is 1. So 1 is the identity, the multiplicative identity when we're talking about numbers. So when we're talking about a matrix, we're going to have something that's similar. We're going to have a matrix that we can multiply any other matrix by and still get itself. And that's called the identity matrix. And the identity matrix is a matrix that has ones down the diagonal and then zeros everywhere else. And so I've written two examples. I've written the identity matrix for a 2 by 2 matrix, an identity matrix for a 3 by 3 matrix. Notice there's ones going diagonally down, and then there's zeros everywhere else. You do want to note, though, that only square matrices have the multiplicative inverses. So if you have a matrix that's a 2 by 3, which means you wouldn't have this bottom row, notice you can't fully get that diagonal because it's not a square matrix. Thus, we can't get the multiplicative inverse. So it only works for 2 by 2s, 3 by 3s, 4 by 4s, 20 by 20s. So that's something to be aware of. Today, we will only be talking really about 2 by 2 matrices, but you can expand upon the material that you learn in a 2 by 2 in order to do a 3 by 3 and above, which is why we're only doing 2 by 2s. So let me slide you down. I'm gonna have to move you back a little bit, I think. Move that desk forward and see if I can just slide you back. Yep. Okay. So the multiplicative inverse, we usually call that A, -1, or whatever matrix label you're using. If you're using a capital B, it'd be B, -1, whatever that may be. But what it is when you take the matrix times its inverse, you're going to get that identity matrix. And it doesn't matter which order you go in, you need to be able to get that identity matrix if they're actually multiplicative inverses. Again, with numbers, you can think about it as what would I multiply 2 by in order to get 1? Well, I would multiply it by 1/2. 2 and 1/2 are multiplicative inverses of each other because when you multiply them together, you're going to get 1, which is the identity. So the same thing, we do the same process for matrices. So when you're working through your homework and doing problems, one of the first ones that you're going to come across is they're going to give you two different matrices, and they're going to ask you to show that B is a multiplicative inverse of A, or vice versa. So in order to do that, you have to show that A times B is the identity matrix, and you have to do that B times A is the identity matrix. Sometimes it'll work one way, but not the other. And so you really need to double check to make sure that they're going to go both ways. Tilt that down. So A times B, we have -1, 3, 2, -5, times B, 5, 2, 3, 1. This is going to be good practice from 6.3 where we learned how to multiply matrices, because this is what we're doing. We're multiplying two matrices, so this is giving you extra practice as well. Remember, when we multiply two matrices, we think about it as in rows times your column. So row times my column. -1 times 5 plus 3 times 2. 2 times 5 plus a -5 times 2. There. Now I'm going to do this and this. -1 times 3 plus 3 times 1. 2 times 3 plus -5 times 1. That gives me -5 and 6, which is 1, 10, and -10, which is 0. -3 and 3, which is 0, 6, and -5, which is 1, which is what we were hoping to get. We were hoping to get the identity matrix and thus prove that these are multiplicative inverses of each other. So far so good. That's half the problem. We did A times B. Now we have to do B times A. Five, 2, 3, 1. Make sure I'm not going off the screen yet. Okay. Same process. Row by column. 5 times -1 plus 3 times 2. 2 times -1 plus 1 times 2. 5 times 3 plus 3 times -5. 2 times 3 plus 1 times -5. So that's -5 and 6, which is 1, -2 and +2, which is 0, 15 and -15, which is 0, and 6 and -5, which is 1. Again, this is what we were hoping to get, because in order to show that B is a multiplicative inverse of A, we have to show that A times B is 1 and that B, or not 1, is the identity matrix, excuse me, and that B times A is the identity matrix. We did that. That means they are multiplicative inverses of each other, which is great. That's what we wanted to show. So this is nice. These are the problems where they give you both of the matrices and they just ask you to verify that they are. If at any point we would have gotten something that wasn't the identity matrix, then we know that they are not multiplicative inverses. So let's go to the back of the room. And I can show you how we actually find the multiplicative inverse when they only give us one of the matrices. Because in this case, we had both. But what if they don't give us the other one in order to verify and we just have to come up with it? Well, then we're going to learn how to do those problems. Okay, I know it's a little angled, but it's kind of the best I can do. So we need to find the identity, or we need to find the multiplicative inverse of this. And it does give me A. And then one thing that we need to remember is that A times the multiplicative inverse is going to give us our identity matrix. Okay? So this is kind of like an equation. We have something we know, something we don't know, and something else we know. So this multiplicative inverse is kind of like our variable. We don't know what the value is yet of that, and that's what we're going to figure out. So I'm going to let A inverse simply be a variable matrix, W, X, Y, Z. So it's a matrix that's just full of variables. That way I can solve for each of those values here in just a few minutes. So I have A, which is 2, 5, 1, 3, times my multiplicative inverse, which is my variable matrix, is W, X, Y, Z. And I know that that's going to equal my identity matrix, which is 1, 0, 0, 1. Okay. Now, once again, I have two matrices and they are being multiplied. I can do that. That's my row by my column multiplication. It doesn't matter that these are variables, I can still do it. So 2 times W plus 1Y. 5W plus 3Y. 2X plus Z, 5X plus 3Z. I kind of think with using the variables, it kind of helps you to identify the pattern of the row column multiplication a little bit more, because you can see that the coefficients of our variables across the rows stay the same, and that's because we're multiplying by the rows of the first matrix. And then our variables stay the same vertically in each of our columns because we multiply by the columns. Maybe that helps you, maybe it doesn't. I think it's neat, and it helps me. Okay, so you might be saying, well, now what do we do? Well, now we have one matrix, and we have it set equal to another. From 6.3, we know that two matrices are considered equal or equivalent if each element within the matrix is equal to each element in the other matrix. That means that from this matrix, I can write systems of equations and thus solve for my variables. I can take 2w plus y, which is here in the 1, 1 spot, and I can set it equal to 1 because I'm saying that this matrix is equal to this matrix. Similarly, my 5w plus 3y equals 0. And there's a system of equations. Two equations, two unknowns. I can do the same thing for my next column. 2x plus z equals 0. 5x plus 3z equals 1. Now this is the same stuff as like from 5.1, 5.2. I need to solve my systems of equations for my variables. The easiest way that I like to do it is with the addition method. So if I'm looking at these equations, the easiest way to do that is going to be to multiply my top one by a -3 in order to eliminate out my y's. I'm going to shift down just a tiny bit so that you can see the rest of the work for this problem all at the same time. So if I multiply this top equation by a -3, I get a -6w minus 3y equals -3. 5w plus 3y equals 0. I just simply rewrote my other equation because I'm using the addition method where I want to be able to have them right on top of each other so I can eliminate a variable. -6 and 5 gives me a -w equals -3. So w equals 3. Now, just like with regular systems of equations, I know one of my variables, so I can go back and I can plug that into one of these equations in order to solve for the other. So if I have 5 times 3 plus 3w equals 0, notice I just took this equation and I plugged in a 3 for my w. 15 plus 3y equals 0. 3y equals -15. Y equals a -5. So I just found those two. Now I'm going to focus on these two equations. Again, I'm going to get rid of one of my variables. It seems like my z's are the easiest one by multiplying this top equation by -3. Very similar process. -6x minus 3z equals 0. 5x plus 3z equals 1. My z's are going to go away, which leaves me with a -x equals 1. So x equals a -1. And again, now that I know one of my variables, I can back substitute. So 5 times -1 plus 3z equals 1. -5 plus 3z equals 1. 3z equals 6. Z equals 2. So what does that tell me? Well, if you remember, and I will shift you back down a little bit so you can see it again. The multiplicative inverse of A, I said, was w, x, y, and z. Well, I just found out that my w was 3, my y was -5, my x was -1, and my z was 2. So I just found the multiplicative inverse by doing this variable matrix multiplying it, and then solving my two systems and two unknowns for the various variables. So this is one method of how you would find the multiplicative inverse of a matrix. This is what I would call the long method. It's still good, it's just long. It does show you though why it works and how it works and all that jazz. However, there is a quick method that I know once I show you, you will never want to do this method again. That's why I show you this method first. So that then when I show you the quick method, at least you've seen the long method, okay? So here's the quick method. It says if we have an A matrix where we have A, B, C, D, so it just has variables because we're doing a generic, then we know that the multiplicative inverse matrix is 1 over AD minus BC times D, negative B, negative C, and A. So what we did with the original matrix was we flipped our A and our D, and then we negated our B and our C. And then obviously we have this number out front, the scalar multiplier. One thing to note is that if the AD minus BC equals 0, if we get a 0 in this denominator out front, that means that we do not have a multiplicative inverse for A, because we can't multiply by an unreal or by a number that has 0 in the denominator. So let's do an example. Here's our A, and we want to find our multiplicative inverse. So you may want to write out to the side that A equals 2, B equals 1, C equals 5, and D equals 3. I know this because A is written in A, B, C, D form, and this will help me to plug in my numbers to find my inverse. So the multiplicative inverse of A is 1 over A, which is 2, times D, which is 3, minus B, which is 1, times C, which is 5, times, now here's where I take my matrix, and I'm going to flip-flop my A and my D, so it's going to be 3 up here and 2 down here, and then I negate my B and my C. Well, this is 6 minus 5, which is 1 over 1. Well, what is 1 over 1? 1. So that simply means that our inverse matrix is this one, which we just found to be true using the long method. This is the exact same answer we just got using the long method, only this is the quick method. And hopefully you can see it's a lot quicker. Doesn't make it right or wrong. This one you can actually get in more trouble with sometimes, because if you flip-flop any of your numbers around, you could mess it up. So if you have to do the long method, this is a great way to check, or vice versa. You could do the long method to check your quick method. So let's do one more quick method, and then we will be done with today. So here is our new A. So again, I'm going to write A equals -1, B equals -2, C equals 3, and D equals 4. Okay? A inverse is 1 over A, which is -1, times D, which is 4, minus B, which is -2, times C, which is 3, times, oops, I have to put my D up to the side. So when I write my matrix here, I'm flip-flopping my A and my D. So that's 4, -1, and then I'm changing the signs on my B and my C. So it becomes a +2 and a -3. Here, this will be -4, and that's +6. So I get 1/2 times this 4 to -3, -1 matrix. Now from 6.3, we learned about scalar multiplication. That's where we have a number out front and we have a matrix. And what we do is we take that scalar and multiply each element within it. It's like distributing. So what we do is we say 1/2 times 4 is 2. 1/2 times 2 is 1. 1/2 times -3 is -3/2. And 1/2 times a -1 is a -1/2. And then this is our multiplicative inverse of A. You can check this by doing A times the multiplicative inverse and making sure you get the identity matrix, and by taking the multiplicative inverse times A and getting that identity matrix. So you could multiply these two together, and as long as you get the identity matrix, you know that you've done your math correct. In the notes page, I do that for you so that you can see that it is correct. But that is it for today. That is all for 6.4 on multiplicative inverses of matrix.